one, you can actually prove to somebody that yes, Apollo people actually did go there because the mirrors are there. You can actually take a laser, shine it, get back, and then you find, yes, the moon is at the right distance, and the moon is receding from us at 3 centimeters a year, all derived from 40 years of mapping of lunar laser ranging. But these mirrors are, so that's very useful. Actually, as a matter, we carried a mirror of NASA's mirror on one of our, on our lander. Unfortunately, now we don't know where it is, but the idea of that was to actually do the laser ranging, not from ground, because they're small mirrors, but from an orbit, to really get very precise orbital determination, which we could have used for multiple missions in the future. But now we'll have to search through the area, locate and see if it's positioned correctly, it can still function as a possible laser ranging station. But it gives you an idea of the fact that in the far side and the near side we're different, which remains a real puzzle in lunar science. It almost looks like two different people designed it, but it may say something about the story of the early phase of the evolution of the solar system. So to study this object, we really need tools, and these tools are rather standard for remote sensing a planetary body. Many of these are also used on Earth. But because this has no air, it allows us to probe it also with certain tools that are not possible for Earth. So radars are very common. You send a beam, look, come back, you derive the position, topography, you can derive the height. You can actually do something further if you send radio waves to the right wavelengths, which are penetrating. The low frequency penetrates the surface, and the lower the frequency, the more it penetrates. You can actually then look for things that could reflect, and water ice are things that can actually reflect laser radar signatures. That is what is being used to really look at presence of subsurface things. And in visible and in infrared, we look at the sunlight bouncing back. That reflection of the sunlight actually has absorption features. Part of the sunlight is absorbed by material that's on the thin surface. It's in the few microns. It can't go deep, but the few microns you can actually see if there is iron present or certain kind of minerals present. It actually produces a signature in the form of an absorption trough, which is then used to map out the presence of such material. You can use X-rays on the moon, not on Earth, because Earth has an atmosphere, but on the moon there's no air, so you can actually do fluorescence as you do. If you go to a goldsmith's shop and you give you old gold, in seconds they'll tell you how much copper is there. How do they do that? X-ray fluorescence. And so we do the same thing, but there's no goldsmith to give you a nice machine. What you have to do is you wait for, that machine has an X-ray source. It shines on your gold, and there's a detector that tells you precisely, all geometry precisely arranged. On the moon, you don't have that. You wait for the sun to turn on. And the sun turns on occasionally in X-rays when it undergoes a flare, solar flare. When it does that, you then look at what comes from the surface of the moon. That same instant, this thing lasts only for some half an hour. In that time, you have to actually see what's the signature. And in that, you see clear signatures coming from atomic transitions of elements. That will tell you this is potassium, this is chlorine, this is sulfur, magnesium, aluminum, and so on. So that's a very important and direct way to measure it. But it requires the sun to cooperate. When we went in Chandrayaan-1, we had one good flare. It's a quiet solar flare condition. It's a beautiful experiment, but it couldn't do anything about it. Again, we actually were in a low solar activity phase. But then on the 10th of this month, there was a nice, beautiful flare. Unfortunately, we were not looking at that time. We were still orienting the spacecraft to the moon, so we missed it. But given the long life now envisaged with the current mission, we hope to really do the first detailed mapping of elements running from sodium, very important element, all the way to titanium and iron, using this fluorescence technique. And then, of course, mass spectrometry. There you can, it's like a fantastic nose that can look for molecules of various types. You can directly measure the presence of water, OH molecules, and argon, and many other things. So synthetic aperture error, as I mentioned, is a very important tool. It's just something that looks off to the side. It's synthetic aperture because you're running a radar on a moving platform. As it moves, it shines. At a different location, it picks up that return signal. Again, it moves. It's constantly pulsing it, and you're taking the return signals, which tells us, as I mentioned, about both the topography, because the reflectance depends on the slope. It also tells you about subsurface content. In particular, the search for water is an important thing that comes out of this machine. Reflectance spectroscopy, as I said, this is wavelength versus intensity of reflected sunlight, and this sort of enhanced features that you see, these absorption dips, are characteristic of each element. So what you see will be a mix of all these things. So it gets a very confusing situation. And your goal as a science person would be to model this thing ensure you're getting a unique solution. It's a very challenging issue. So to do that, you often have to go back to a laboratory, actually say, all right, I'm going to now take, say, known samples, create the same angle. Even the angle of at which the sun ray comes in makes a difference. So that phase angle is very critical. So various phase angles, various temperatures, you have to really derive reflectance. And then look, what is the combination of things that give rise to the integrated signal that you see? Quite a challenging thing. Today we have, for example, there are laboratories that do this. We're now working with the German DLR laboratory to really look at, they have specialized laboratory where these things can be taken to very high temperatures, because we want to study this also for the moon, for Venus, where the temperatures are 750 degrees Kelvin. So at high temperatures, this emissivity profiles will change. So there's a direct linkage between laboratory exercises and the kind of interpretation that you have to do when you get data from the moon. Here is the famous signature of water, which is this absorption feature.